Noah, I'm going to put you on the spot. Let you read the antitrust compliance statement.
Perfect. Yeah, thanks, Jeff. The Advanced Water Heating Initiative, AWHI, is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocating markets for customers, or promotion of a particular product or accessory.
Awesome. So I think, Noah, this is your slide as well.
Yep. So AWHI updates, not a whole lot right now, but I've talked about the load shifting study repository before here. So basically just a whole bunch of different studies from across the industry. So everything that I found and that folks here have kindly sent me, that's going to be hosted on AWHI's website very soon. So just be in a little one-pager format, kind of advertising what it is, and then a link to the main repository and a description of what can be found there. So that'll be up in the next month.
Thank you. Okay. Peter and Noah, you're going to do this. We were talking about doing some brief introductions. I wanted to give the floor to people who have never been on before and give us a little bit of background about yourself. If you've already been on, don't worry about it. But anybody new to the organization, new to this meeting today, don't be shy.
Okay, I start. It's Victoria Otto here from Bosch Home Comfort. So thanks for inviting me.
Great. Glad you're here. Anyone else? Okay, so I'm going to drop sharing, and Peter, I'm going to ask you to start running it from your end.
Sounds good. Can do. There we go. Okay, can you all see my screen now?
Roger, Roger.
Great. Okay, so this is a presentation that Noah and I gave at the ACEEE Hot Water Forum a few weeks ago, and it's talking about some work that we're doing performing field monitoring of advanced load shifting controls for 120-volt heat pump water heaters. And we'll get into what that means in a minute. First, as context, we're doing this work in the context of the Cal Flex Hub and Store for Build projects, with additional match funding from some of the utilities to help support, a deeper dive into it and more field monitoring efforts. So Cal Flex Hub is a California Energy Commission funded project led by Lawrence Berkeley National Laboratory, where we're really building a consortium of academic and industry partners to really advance the state of the art in controls for products that automatically shift load in response to electricity prices. It's working in the context of highly dynamic prices, so you could envision the price of electricity being different literally every hour of the year in a way, and these prices would be structured to encourage people to shift load in the ways that balance the utility grid and make sure they can reduce their utility bills by doing so. And one project or one technology we're studying in that project is heat pump water heaters. How convenient. We're also doing it in the context of Berkeley Lab's Store for Build project. This is a Department of Energy funded project, and it's a consortium of many different national laboratories pursuing a number of different projects that are all about advancing the state of the art of thermal energy storage in buildings. And while many of the projects focus on things like adding phase change material storage to heating and cooling loads, we also think it's really important to focus on leveraging the existing thermal energy storage because it's already there, it's no cost. And so one example of that, quite conveniently again, is load shifting with heat pump water heaters and just making use of that storage, energy storage that's already available in the tank. So these next two slides provide some background, and it's mostly things that I presented at the Hot Water Forum last year, but there's really a challenge here in load shifting with heat pump water heaters, a couple of different challenges. One of which is just that it's kind of hard to do well. right? One of these studies that I previously worked in, we implemented load shifting using a manufacturer API that allowed you to directly change the set temperature. And we originally kind of naively assumed that we could just suddenly increase the set temperature and they would use the heat pump to shift load. But in doing so, we increased the set temperature too much. The onboard controller thought there was a risk of hot water runouts and sending cold water to the occupants. And so it used the resistance elements instead. And so, right, in order to do this well, we really need to understand a lot about how the heat pump water heaters work, how they respond to these different signals, and make sure we use the signals intelligently. Simultaneously, if we're looking at this from the point of view of, say, a utility program like PG&E's Water Saver or Southern California Edison's Smart Shift, they don't really get much information to work with, right? Heat pump water heaters do not include flow meters, so we can't see historical hot water consumption. And even if they did, at least at the single family residential scale, hot water consumption is pretty random and varies a lot from day to day. So even if we knew what people did historically, we may or may not be able to predict what they would do in the future, right? And so now it gets really hard to customize these controls to different on-site behaviors without the information that we might need. All of that said, we do believe that you can pick out some differences between homes, at least in terms of what's pretty typical. You could envision, and looking at the plot on the right, we have an example of how we could work with that. But you could envision 3 different homes, like we have plotted there. The top plot shows the hot water consumption of these 3 different homes in liters per 15 seconds, which if you do the unit conversions actually works out to be pretty darn close to gallons per minute. But we've got 3 different draw profiles. And the first one, let's talk about this green line, where they're a very high user of hot water in the morning. And because they use a lot of water, presumably taking a number of showers in the morning, if you look down at the electric demand plot on the bottom, you can see they withdraw water from the bottom of the tank, which causes the heat pump to activate right around, I would say, 7:30. Then the heat pump continues to operate, heating the water in the tank, but the occupants continue consuming hot water faster than the heat pump can reheat the water. And so eventually there's a risk of a hot water runout, and that heat pump water heater does switch to using the electric resistance element. Now, if we look at the blue line, we can see very similar things, but shifted later in the day. They use a lot of hot water in the evening. In response, the heat pump kicks on, but it can't provide enough heat and there's a risk of a runout, so the resistance elements kick on. And then if we look at the red line, we see a third very different case where there's actually 0 hot water consumption that day. Presumably somebody's on vacation and the heat pump activates twice to recover from the jacket losses, and there's very little load here. So you could imagine that if you are using these load shifting signals, for the sake of this presentation, we'll focus on CTA 2045, you would need to send them in different ways to optimize the load shifting performance for these 3 different homes, right? The green one would need an advanced load up probably around 5 or 6 a.m. to really maximize the energy stored in the tank. And at the very least, avoid that electric resistance operation in the morning, but maybe also be able to avoid heat pump use in the morning and kind of eventually shift that presumably towards the midday and towards overnight. The blue line, same thing. It needs that advanced load up signal, only it needs it around maybe 3, maybe 4 in the afternoon. Correct, Jackson. The plot shown here is for 240 volt heat pump water heaters. That's a good correction or a good clarification. And then the red line, pretty much all we can do is make it consume more energy. So we really just shouldn't do anything at all for that one. So we do need to find some way to kind of customize these signal strategies to different behaviors. And so that's what LBNL has been working on. And we've created a way of breaking heat pump water heaters out into groups based solely on their baseline electricity consumption profiles, right? Because again, we don't have hot water consumption. We have to work with what we can get. And from there, we create these different groups. And then we run an algorithm that looks at different load shifting control strategies to customize a schedule of signals that get sent at different times throughout the day. And so that's what this plot up top shows. You can see 4 different groupings of heat pump water heaters and schedules of what CTA's 2045 signals get sent at different times of day. And if we do that, at least in this, so this so far is all simulation work that was background to field studies. But if we do that, we can customize the load shifting schedules to different price curves, such as the one that we're using in CalFlexSub shown here. And we can create a dramatically different electricity consumption profile. So in this bottom plot, the red shaded periods are times when the electricity price is above average. So we want to shift electricity consumption away from those times to the white background times. And also, California has a significant problem with overproduction of solar electricity around midday. So that's why you see the price of electricity is lowest at that time of day. And ideally, we would shift electricity to that time of day. And you can see we're getting that result. If you use the standard manufacturer control logic that does not include price response and it's, feedback based on the temperature of water in the tank, you get the blue line where, there's a bit of consumption overnight, then there's the shower rush in the morning, which conveniently that electricity consumption does line up pretty well with the solar production in California. And then you get some electricity consumption in response to hot water use in the evening period. But if we use LBNL's algorithm to come up with the CTA 2045 signals that minimize the operating cost, we really shift a lot of all that load right to the midday period when electricity prices are cheapest. And the results that we get, at least in these simulations, is that we were able to shift 77% of the peak load to low price times. And because of that, we were able to reduce the electricity cost of operating these heat pump water heaters by 29%. So there's a lot of potential here. And some of the methods you can see up here, these are things we're pointing out because we're trying to make this something that utility programs can easily implement, or that manufacturers could include the logic for right on their products, right? So when the prices go out, the utilities can run the simulations, generate the signal schedules, and send the signals to their fleet of water heaters. Or the prices could be sent directly to the products, and if manufacturers have similar logic, the products just know what to do and they can minimize the operating cost for their customers. So that's all background, talking about the algorithms we created. Now Noah and I will shift to talking about the field study with 120 volt products that we're working on. And Noah's up.
Awesome. Thanks, Peter. Phase 1, which I think I've talked to most of you about if you've been on these calls before, and if not, just a little bit of background. Back in 2021, NBI oversaw the installation of 32 heat pump water heaters throughout California in a bunch of different climate zones. And we monitored that data with help from KW Engineering for 12 plus months for all of those sites. So got a ton of data focused on just validating that heat pump water heater performance, making sure they were saving as much energy as guaranteed in the manufacturer specs. They were performing up to par, and most importantly, people were getting hot water and they were not thinking too much about their heat pump water heaters, meaning, they're getting the hot water when they needed to, weren't getting runouts, all that sort of deal. And we did periodic surveys throughout the first round of that study. And overall, as you can see by the chart on that bottom right side there, people were very satisfied. In blue, it's showing, very satisfied or satisfied. And then red is showing orange is when it's dissatisfied. And, really the only things that came up were some vibration and noise. They do make around 55, 60 decibels of noise. So if they're installed in an inconvenient location, that can be a bit annoying, but overall, very satisfied. Not too many hot water runouts. And then next slide, Peter. So next, after that concluded back in July of 2023, and we published our findings on the performance of these new 120 volt heat pump water heaters, we shifted our focus to load shifting, which is, obviously the focus of this working group, and wanted to see, okay, yes, these things work. That was the first step. Now, can we move on and say, can they successfully shift load as well? And Peter just gave some of the background on general heat pump water heater load shifting, but a lot of the work done in the past has been on 240 volt water heaters, right? That have large backup resistive elements and, have that kind of flexibility to ramp up and quickly heat up a bunch of water. So we wanted to test how this worked for 120 volts, which either have no backup resistive element or a much smaller one around 900-ish watts as opposed to 4,500 generally for 240 volts. So a lot slower to reheat water and thus needed a different algorithm to do their load shifting. So kind of the goals for this study were understand variations in day-to-day hot water draw. So how well can you predict a user's hot water consumption based on past hot water consumption, right? Do people take showers at a similar time of different days? Do they run the dishwasher at a similar time, right? To be able to create a kind of a uniform load shape from day to day. We also wanted to identify hot water use patterns without detailed monitoring. Peter was talking about this, right? But most water heaters, just generally speaking, don't have flow meters. They don't have thermistors, right? You don't have all that information. So we were trying to figure out, can we do this? Can we get enough data just by using universal control modules with CTA 2045 that can give us energy consumption, or at least, watts instantaneously, but without having all the rest of kind of that backup data to confirm what's going on. And then lastly, we wanted to create these custom 120 volt controls because they are different than 240 volt, like I was saying. Next slide, please.
Okay, back to me. All right, so I did talk previously about how a lot of the method we are using focuses on identifying homes that have typical baseline behavior and putting them into groups so that we can customize the signal schedules for each of these groups. And prior to getting out into the field, we've been doing this with 148 simulated heat pump water heaters. And really, it's 148 with different monitored hot water draw profiles. So the same product, but in different homes, basically. And our old highly preliminary method of grouping the heat pump water heaters was just to look at the average number of kilowatt hours of electricity consumed per day. And you can see in some ways this worked pretty darn well, right? If you compare plots 2 and plot 3, you can see that all of the heat pump water heaters that use the electric resistance elements are down in group 3, which means that we'll be able to identify that you should really use the advanced loadup command for group 3, certainly much more than for group 2, so you can avoid using the resistance elements. But if you look at plots 1 and 2, you can really see that this was not at all differentiating between users based on the timing of their electricity consumption, right? Plot 1 just shows heat pumps running at any time of the day. There's no grouping. So this preliminary method needed some refinement. And one thing we did in this project was switch to grouping them based on the root mean squared error. And root mean squared error is a metric that looks for differences not only throughout the entire day, but at every single time step within the day. And because of that, it really identifies water heaters that have electricity consumption at different times of day. The end result is that, it still differentiates between really high users and really low users. And again, you can see that all the users or all the homes that use electric resistance elements show up in the same group as shown in plot 6. But it also now is really sensitive to the timing of electricity consumption. And you can see in plots, well, all 3 of the plots, that the consumption of electricity is really close together. And so the homes are using electricity at similar times of day as well, which really helps us do a better job of customizing the signals based on people's typical behavior. So from there, let's step back a little bit and talk about how we're starting to customize these controls to the 120 volt heat pump water heaters, which has to be based on the differences between the 240 volt products and the 120 volt products. I'll highlight, since I've given this presentation a few times and literally every time been called out on this, These are fairly representative schematics. They're not intended to accurately match any particular manufacturer's products. And specifically, the image for the 120-volt heat pump water heater shows the condenser in the inside of the tank, right in the middle. To our knowledge, that's not the case. That condenser is still wrapped around the outside of the storage tank. We're aware of that. But moving on, so the 240-volt products have most of the components of the heat pump up at the top, stored on top of the tank. Then they have the storage tank on the bottom, which contains roughly 40 to 80 gallons of hot water. Then the condenser coil of the heat pump is wrapped around the outside of the tank and is the primary heating element. Then they have two separate resistance elements and two thermostats, one at the top of the tank and one at the bottom of the tank. And that's pretty key. Remember that. One at the top, one at the bottom. The 120-volt products also have most of the components of the heat pump on top of the storage tank. Then they have a storage tank that holds 40 to 80 gallons of hot water ready to go for use. The condenser coil is wrapped around the outside of the tank, not in the middle as shown here. Then they typically have one thermostat at the bottom of the tank. This is not true for all manufacturers, but we're certain it's true for the manufacturer that we are working with. They also typically do not have electric resistance elements, though one manufacturer does up at the top. Then they also have an integrated mixing valve. So the temperature of water that the occupant specifies is the temperature that comes out of the mixing valve, not necessarily the temperature of water that's stored in the tank. And manufacturers change the temperature of water stored in the tank to increase the amount of energy that's stored and available to the user. And that does impact how we can perform load shifting with these products. Then I always forget to click forward, but yes, they have an internal set temperature that might differ from the integrated mixing valve. Okay, thank you for pointing that out, John. The Rheem dedicated unit does not have an integrated mixing valve, presumably because Rheem's confident that the larger heat pump will recharge the energy stored in the tank rapidly enough and the mixing valve's not necessary. Okay, so let's look at the implications that these different design changes have on load shifting performance. And let's start with the assumption of a 240-volt water heater with 50 gallons of storage. The user has specified a set temperature of 125. To implement load shifting, we temporarily increase that set temperature to 140, either through an API changing the set temperature or through a CTA 2045 advanced loadup command. Now, our field observation from prior projects is that these heat pump water heaters will only heat water in the tank if the upper temperature is below the set point. So if you heat all the water to 140 degrees and then reduce the set temperature later back down to 125, that means that it will only activate the heat pump if that upper thermostat records water temperatures below 125. This means you can extract about 80% of the water from the storage tank prior to the heat pump activating. And with those assumptions that I listed, you can withdraw about 7 kilowatt hours of thermal energy in the form of hot water and shift about 2.3 kilowatt hours of electricity consumption. Now, there are pros and cons to this, right? From the utility point of view of shifting load, this is excellent. You can shift a lot of load through these heat pump water heaters. From the occupant point of view, though, if you're that aggressive on your load shifting, there's a higher chance of runouts and people getting cold water, which the occupants will not appreciate, and which will probably cause them to leave the program, which the utilities will not appreciate. So, there's some optimization to do around this, I think. Now, if we shift over to the 120 volts, let's assume it's the same 50-gallon storage tank. Let's assume that the manufacturer uses an internal set temperature of 133 degrees Fahrenheit in their 50-gallon units to increase the amount of energy that's stored in the tank. Let's assume the occupant set a 125-degree set temperature on the mixing valve. And let's keep that same inlet water set temperature of 65 degrees Fahrenheit. Now, the real key here is that since this 120 volt product does not have an upper thermostat, the heat pump's going to kick on when the lower thermostat notices cold water, which will occur when roughly 20% of the water is extracted, which means you can withdraw about 1.7 kilowatt hours of thermal energy and shift about 0.55 kilowatt hours of electricity consumption, which isn't as much load shifting, but it also doesn't cause the same risk of runouts, right? So we've got some analysis to do on what's the best way to control these things in that regards, I think. Now, moving back to our field demonstration, Noah's going to talk about how we recruited sites.
Yeah, thanks for all that background, Peter. So just a little bit more on the study itself. We were recruiting from the pool of original 32 participants, and only some of them qualified. We had 3 manufacturers, but 2 of them were kind of more in the beta testing phase, and thus, we just wanted to do the field validation and not do the load shifting component. So we just focused on 1 manufacturer. And then, so we wanted to make sure all the installs went as smoothly as possible for those people who did opt in. So, shout out to SkyCentrics there for providing initial UCM documentation, and then we kind of went further for 120 specifically because people hadn't been installing UCMs on 120 volts too much yet. So basically, just made some bespoke instructions there, and then there was some help necessary for getting folks up and installed. The actual process for putting a UCM on is pretty simple. You unscrew a couple of screws and just put it, like, you're removing a cover plate on the 120 volt heat and water heater itself because it already has a built-in ECO port for the newer modules. So, and all you're doing then is taking that little white device, taking the screws off the cover plate and putting it on top. The more difficult part was actually getting them connected online and getting data going. Like anything else, right, it requires a connection to Wi-Fi. Sometimes that can create some finicky instances, and then there's also just some user error, right? Even if you set up perfectly good instructions, if there are 10 plus steps, right, people are just going to get a little bit confused. So that is just something to keep in mind for future programs where it's important to anticipate some staff time for getting these things set up. And it's also important for thinking about scaling, right? Because we only had 12 participants, but if we were getting up into the thousands, me as a single person couldn't be talking to all those people who had setup difficulties. So getting it as streamlined as possible, especially on the connection front, is going to be pretty critical. Next slide. Yeah, so just some in terms of lessons learned, as I was talking about, right, installation of the actual device itself is pretty simple. So that is awesome. Anybody who can unscrew a screw can basically put it in. But then, yeah, so you got to essentially put in a URL, put your device code in, all that sort of thing. Make sure the device is showing the proper color to make sure it's connected to the internet. And then since we were using SkyCentrics, there's a cool portal there where it can log in and see, yes, this device is showing up online. But again, some people got confused, I think, especially by having to enter a URL into, like, how when you're on an airline and you have to go in and go to United, even though you don't technically have internet, that'll like load specifically the United site. That's basically the analogy I've used with people for doing these installs, where you have to put in this HTML code into your browser, and people are like, "Oh, I don't have internet. Like Safari doesn't work, but like, why is this internet?" So it only works for that one thing, and then they're switching back to their own Wi-Fi. So I think the kind of barrier to entry there can be a little bit confusing, but I think putting it in analogies like the, United Airlines, American Airlines type deal will help people become more familiar. So I think getting it from the technical to as much layman terms as possible is going to make this more cost effective too, because the more people who need help, that's time is money for doing these phone calls. So I think it's just wanted to make sure that lesson learned was in there. And then participant follow through can also be problematic sometimes. Even if people say yes, they want to be part of a study, they may decide to just no longer respond to emails. Or we even had one person who they said, yes, I want to participate. We sent them a module. Once the module was delivered, they say, actually, I don't want to participate any longer. So we had to go through an arduous process of getting the $150 module back, finding another person to take their place in the study. So all that sort of deal. It's just important to keep in mind because yes, even the technology works, and even if the load shifting works, there are still people problems to deal with. So I just wanted to put that in there as we think about scaling up. Next slide.
Okay.
So back to you,
me.
Peter.
Yes. Okay, so this project that we're doing with 120 volts is a field study project, not only simulation. So this slide here talks about some of the research questions that we are trying to answer and when testing is occurring to start to address those questions. You can see that some of these are now in the past, so we do have some data to share. But the first question is, how do these products perform in terms of load shifting if we do not use the advanced load up command? And part of what's driving that is we've heard from some people rumors that they do not respond to the advanced load up, so that's not an option. But also coming back to the set temperature, the internal set temperature challenge, if the internal set temperature of a 40-gallon 120-volt heat pump water heater is 140 degrees, and just to clarify, I do not know that for a fact. We have to sign an NDA to get that information, and we haven't gone down that path at this time. But if it is 140, then the heat pump water heater can't actually take the water in the tank much higher than that anyway. So advanced load up just doesn't really have much that it could do. Um, and so we ran a week of testing where we customized the CTA 2045 signal schedules, assuming that we did not have access to the advanced load up command. And then we sent those signal schedules out to the water heaters in the fleet so that we could collect data showing the load shifting performance. Then we decided just to test it, we would assume that they do respond to the advanced load up command. We generated new CTA 2045 signal schedules. We sent them out to the heat pump water heaters and we collected data showing the performance. This third row has been a little bit delayed, unfortunately, but we also want to explore the question of how to best do this with current utility time of use prices. Right? These prices create different economic incentives compared to the CalFlex Hub research prices. And so we wanted to figure out, will the occupants shift as much load in response to these time of use rates or not? Do the occupants receive as much economic incentive for shifting their load or not? Do we end up with similar signal schedules? And how does this impact the smoothness of the load curve? So we're going to choose one of the two controls from the first and second tests, depending on which one performed best. And then we will generate new signal schedules in response to the time of use rates, and we'll send them out to the heat pump water heaters in the field, and we'll see how they do. So we have some preliminary results from the first two tests here in the presentation. We don't have a slide on the tests with advanced load up because, well, that was actually just barely before the hot water forum, so we hadn't yet had a chance to analyze the data and include it. So I'll just cut to the chase on that one. These heat pump water heaters did not respond to the advanced load up signal. So we have started conversations between the UCM manufacturer and the water heater manufacturer to figure out what's going wrong, figure out if this is intentional or if this is a mistake or a problem, miscommunication at some point in the chain, and figure out how to best respond to this situation. But stepping further back to the week without advanced load up, we do have preliminary field monitoring results that show how this performed. At the time of the test, we had 8 participants in the study, and so the results show what happens with 8 participants. And we used a baseline period of 3 weeks and then averaged across all of the weekdays in that period to identify the typical baseline behavior. Then we had 1 week of testing with the CTA 2045 signals, and we averaged across the weekdays during that testing week to identify the testing behavior. And so this plot is the same format as before. So the pink shaded periods are, Jeff will come back to that one in a second. So the pink shaded periods are times when the electricity price in the CalFlex Hub price schedule is above average. So we're trying to shift load away from there to the white periods. The blue line is the behavior in the baseline with no load shifting, and the green line is what happened with load shifting. And so you can see we had two separate load up periods. The timing of the load up commands did vary a little bit from group to group, but they're pretty similar in that they all had a load up period around 3:30 to 5 in the morning, trying to pre-charge the tank before the morning shower rush, and a load up period around 10 to 11 in the morning, pre-charging the tank prior to the electricity price rising, as it gradually rose through the afternoon and into the evening. Then we had two shed periods, which they actually lined up quite well with the times when with the red shaded periods, because they're trying to coast through the high price periods without consuming electricity. And you can see two or a few high level findings from this. One is that 0 kilowatt hours consumed during the evening high price period. So we just shifted that load, which we were somewhat surprised by, but also very pleased by. So that was excellent. Unfortunately, we were not able to shift all of the post-shower consumption out of the high price period. Just not having access to advanced load up limited the amount of energy that we could store in the tank, and we couldn't store enough in the tank to coast through or to, provide all that hot water for the showers without the heat pumps having to kick on to recover heat in the tank. And so we did have some heat pumps kick on right then and consume electricity when the price is high. So that's one thing we want to keep working on. But, all those results showed that we reduced the cost of electricity of these heat pump water heaters on that day by 27%, while shifting load in ways that are beneficial to the utility. So we're kind of creating a win-win situation where the occupants get a benefit and the utilities get a benefit. And now I saw Jeff put a message in the chat, so I will pull it up. So Jeff, I don't think I know Bob Bass, so if you could provide an introduction, that would be very helpful. Aside from that, yes, I'm happy to have that conversation.
Yeah, Peter, we've exchanged a couple emails a couple months ago, I think, but I'd be glad to chat with you.
Yeah, I think I remember that. Good point. So let's follow up on those emails and schedule a meeting and a chat. How's that sound?
Yeah, for sure.
Okay, so Tristan, you've got a number of questions. First one, the load up stopped quite a bit before the morning pink bar. Would a load up closer to the pink have helped? Yes, it probably would have. And one challenge that we're having, the control algorithm is only sensitive to the changes in the price curve. And we're kind of noticing that when you apply the same response to the price curve in the morning as in the evening, you don't necessarily get the optimal response in both the morning and the evening. So we're starting to think about ways to improve the algorithm to be more sensitive to the time of day that way. Okay, your other question, the tanks report storage capacity. Did the advanced load up drive that to 0? And did it stay at 0 before the pink morning bar? So we actually haven't done that analysis. We should go back and do so. One clarification, this was assuming there was no advanced load up, so it was only using load up. Based on how load up is supposed to behave, we're under the impression that it would drive the take value to 0. And then presumably people consumed a little bit of hot water or there were some jacket losses. So it probably actually was not 0 anymore by the time the pink bar started. Okay, and we've got one more question. Have you also looked into delayed load up after shower? I don't entirely understand that question. Could you
Maybe I can
jump?
elaborate. I guess it's not a CTA demand right now, but I was just wondering if that was ever been discussed in that standard, because as you see that there's a post-shower consumption, because I guess that's because it's empty and the heat pump just wants to get back to the set point, and that's why it's loading up immediately. But is there any
Okay.
discussions in delaying load up, just because the user will not use the water heater at noon?
Sure. Okay. So you're talking about when they come out of shed mode and the tank is colder than the water heater wants it to be, and all the heat pumps suddenly activate to recover, right?
Yes. Yeah.
Okay. So I would say there have been conversations around it, but it hasn't yet become the top priority, which, I mean, you can see from this plot might be a problem, right? Suddenly there's a large demand or large increase in demand as all these heat pumps reactivate, which could be really challenging for the utilities to handle. Um, you also see similar behavior when we send the load up signals, just in terms of there are these sudden spikes as several heat pumps activate. And we have worked on an algorithm where you can phase in the load up command depending on the state of charge of the tank. And that's how you can start to get a smooth ramp instead of a sudden spike. And so we've shown it works well in simulation. The next steps on that algorithm are working with utilities to figure out what the ramp should be, or creating an algorithm where they can state what ramp up they want, and then the algorithm automatically adapts. As well as working with the communications, manufacturers or providers to make sure that their front ends are capable of implementing that particular algorithm. Tristan, you've got a hand up.
Yeah, I just want to say that the fact that we're getting that storage capacity number is obviously super helpful, right? Like you said, right? We can make sure ideally every tank's zero right before that pink morning bar. That means they're fully loaded at least right there. Best chance of avoiding coming on during the pink morning bar, and then feathering the load ups based on that storage capacity number, feathering them afterwards to make sure there's not a big snapback. I mean, all of that is thanks to the internal prediction of what their storage capacity is. And thanks to Bob Bass, we're also learning which manufacturers are doing a good job of predicting their storage capacity, which is super helpful.
Yep, great. Thanks for those additional comments. Totally agree. Bob, you had the question of, could the algorithm anticipate price? We're not assuming that it, predicts what the price is going to be for the next 24 hours. So far, we're assuming that the utility or CAISO or some organization like that sends out the price for the next 24 hours. And so it just takes it as an input rather than trying to estimate what it's going to be.
Yeah, but a little bit of look backwards could give you a little look forward, right? If you're trying to see where you're going to get into that crossing point, where that pink line is going to be for the day, you could get a little picture by doing a slope, a simple linear slope that would maybe allow you to turn on that advanced load up a bit earlier, or a bit later than you anticipated. It doesn't have to be 24 hours. It just could be just an hour or two ahead.
Yeah, possibly. And so I'll, point out that we are assuming it gets 24-hour electricity prices, and then those are set in stone. They don't change until the next day when we get the next 24-hour prices.
Okay, got it. Never mind.
Okay, so I see we're running over time, which is amazing because this was originally a 10-minute presentation and we've now gone longer than 30. So I'll cut to the last slide before we go back to conversations. But this is really the development and deployment roadmap that we have in mind. Originally, we worked in Cal Flex Hub and Store for Build to develop the control logic and perform simulations showing the potential. Now through Store for Build, we're developing what I call an easy access tool chain. These controls currently have the problem that I'm the only one who knows how to do it, which is really not going to work for deployment. So we're working on creating tools that are, shall we say, more user-friendly than the current options that utilities can leverage. And we've talked to PG&E's Water Saver program. They're interested in being alpha testers on these tools and giving us feedback on how well they work, how user-friendly they are, whether there's something that PG&E can deploy in their programs. So we're really looking forward to getting that feedback. Simultaneously, we have a small lab testing project with Southern California Edison that's starting. And we also have a proposal to Southern California Edison to do some pretty deep lab testing projects. So those would be very helpful. On the technology transfer side, we have created a working group with several different organizations, mostly running utility programs to have some knowledge transfer conversations going both ways, right? We act as the think tank coming up with the advanced load shifting controls. They act as the people with boots on the ground that knows what really happens in buildings and can help make sure that we stay grounded. And hopefully we meet somewhere in the middle, and so we can create things that really help them put out the best programs. We also currently have this field study underway, and all of this is working towards the goal of including controls such as these in widespread utility programs. And that's our last slide.
Thank you so much, Peter. Really appreciate it. And I'm glad there was so much enthusiasm in terms of questions. Let me just look in the chat again and make sure we didn't miss anything. But yeah, would you actually quickly remind everyone what store for build is, Peter, in case people don't know what that is?
Yeah, so Store for Build is a Department of Energy funded research project that's being pursued by several different national laboratories, and it's all about advancing the state of the art in thermal energy storage for buildings. There are a number of different projects, some looking at phase change material storage added to rooftop units for commercial buildings, or phase change materials in the envelope of buildings. LBNL has several projects focused on combining heat pumps with thermal energy storage, such as, space conditioning systems with air to water heat pumps, or such as heat pump water heaters, which is how it applies to this conversation today.
Wonderful. Does anyone else have any further questions?
Yeah. Hi, this is John Colliner. The whole process did remind me of, I've worked with the shifted energy product before for load shifting for water heaters. Are you aware of that product?
I'm aware of it, yes.
Yeah, I was just curious if we're chatting with them because they're it's a AI load shifting water heater thing.
Yeah, I had a few conversations with them back in the day, but it didn't really take off, unfortunately. Maybe we should revisit that.
Yeah, always good to have cross-industry collaboration for sure. Many lessons to be learned. Thanks,
Absolutely.
John.
And Jeff, you had a comment in the chat that I would just like to second. You were commenting that the primary goal is hot water for the customer, right? So we need to make sure that any load shifting we do does not interfere with that. And also you commented that the study can inform manufacturers and how they can best, provide load shifting services to utilities. And I'd agree with that too, right? While we're focusing on utility programs, that may or may not be the best way to go forward. And maybe manufacturers hosting controls right on their products, which, maybe we can help them develop if they're interested. Maybe that's the best way forward.
Yeah, Peter, thank you. I got to remember that we're providing a service called hot water, and I love to take a hot shower in the morning. I do not want a cold water run out. So,
right.
Yep.
Nobody does.
Yeah.
Exactly. Yeah, the first and foremost thing we try and emphasize is that people should notice this is happening. There are a few people in our study who, are curious and want to nerd out a little bit, but that is the vast minority. Most people, if they have a load shifting going on, do not want to know it's, do not want to notice it. It's obviously important for them to be aware because that is consent that they're part of a program. But if they're aware of it, it probably means they do not have hot water.
Yeah. And that's part of why we think the advanced load up command is very important, because you can use that to increase the energy stored prior to, showers. And in that way, you can actually reduce the risk of a cold water run out. Whereas without it, you have to shift load using only shed, which increases the risk. That's not good.
Mm-hmm. Yeah, and you mentioned jacket losses, Peter, and I feel like I know we're almost out of time, but do you think you could speak to that for a second and just I guess if we did have advanced load up, do you think we could shift the time back more than an hour or two ahead of the scheduled demand period, or do you think jacket losses would be too severe, let's say for 4 or 5 hours in advance?
I think that's part of the advantage of customizing to different use patterns. So with the advanced load up, you would probably have to shift it further back just because that requires more heat pump runtime to get up to the new set temperature anyway. But there is the downside that the higher temperature water in the tank increases jacket losses, increases operating costs. And so I think we would find, well, in simulation, we have certainly found that some groups really benefit from advanced load up. And other groups, you actually want to not use it because you can coast through the high price periods without using it, and using it would only increase the operating cost.
That's a great answer. Thank you so much.
Hey,
All
Jeff.
right, y'all. Well, we are almost at time here. So just in terms of next steps, there is, one of these meetings that happens every month. We have another cool field study discussion on May 3rd, so definitely be there for that. This meeting was also recorded, so it will be actually posted on YouTube. Just wanted to make a note that we are shifting from just recording these and sending them out via email. HPWHs has a new person working on our YouTube, so this will get posted and be much easier to share than having to work with a finicky link that likes to sometimes forget it has permissions shared with everybody. So that'll be more convenient going forward. So anyway, yeah, expect a follow-up email from me. We'll include the slide deck. We will include the recording. And then once the YouTube link goes up, I will start sending those out as well. Yeah, so thank you everybody for coming, and hope to see you on May 3rd for the next session.
I think Tristan had something you wanted to add.
Oh,
Go
sorry,
ahead,
Tristan, go ahead.
Yeah, no problem. I just figured with the last 2 minutes, Jeff, is there anything you wanted to update everyone on sort of connectivity discussions with AWHI for commercial?
Yeah, I would say I think that's sort of the next frontier for us. We've got a white paper that's coming in from Ecotope that did a working session, and it really focuses on CTA 2045B level 2. There are some other attributes about central systems that are a little different than a unitary residential, but be aware of that. AHRI 1530 is exploring this as well, and there's some conversation about the word or rather than and. There was a question brought up that was we want to have an open ADR and not require CTA 2045, and I would think the utilities would weigh in and say no, it needs to be CTA 2045 and open ADR or and other methods. But I just wanted people to be aware of that conversation going on so there's full transparency. I'd also wanted to give a brief update. We're still trying to get the details ironed out of a security document or security paper for CTA 2045 through Portland State University and Oregon State University. That's squarely in my court. PNNL has said, yes, they're interested in reviewing it, but they don't have bandwidth right now to craft it. So we've pivoted and we're working with universities to help out with that. And then the last one here in the Northwest, we've got 10 very active utilities looking to go to scale for CTA 2045 with water heating and then also space heating. So stay tuned and I'll try to get you some updates in the next session or two. Peter, thank you very much for your great presentation. Nice work. Noah, thank you as well. It was well attended at ACEEE, and I think it's probably going to create a lot more continued interest.
Excellent.
Think
Yeah,
so.
thank you, Jeff.
Yeah,
and thanks
thanks for
again,
the
Peter.
opportunity.
Sorry.
No, I didn't mean to talk over you, but thanks for the opportunity.
Yeah, awesome work.
Absolutely. Yeah, I was super glad that you got to go more into detail this time. But yeah, thanks again everybody for being here, and look forward to the follow-up.
We'll see you all next month.
Sounds
Bye.
great. Cheers.